Hi, today let's understand about the bigO notation in practical terms because this is one of those concepts that shows up everywhere once you start building real software. If you have ever wondered how applications like Instagram or Facebook can handle millions of users without slowing down, while other applications struggle at much smaller scale, bigO is a big part of that answer. At its core, bigO is just a way to describe how an algorithm's performance changes as the amount of data grows. And by algorithm, I simply mean a set of steps your code follows to solve a problem. So instead of focusing on abstract math in this video, we are going to look at how different choices behave as systems grow. We'll come back to mathematical side of bigO in a future video. Let's start with the basics. In bigO notation, we use the letter n to represent the size of the input. Depending on the situation, n could be the number of users, number of photos, the number of records in a database, or really any collection code is working with. bigO asks one simple but an important question. As n grows, how much more work does the algorithm have to do? Let's understand this with real examples. Let's start with the login system. When you type your username, the application needs to find your account. Have a look at this method. This function loops through all users one by one. It compares each user's name with the username we are searching for. If the match is at the end of the list, the function has to check every user. This worst case behavior is what makes this bigO of n. Understand it this way, if you have 1 million users, the worst case is 1 million checks. Now imagine that you are the millionth user in the system. Your username happens to be the very last one in the list. When you try to log in, the system starts at the first user and checks every single entry until it finally reaches you. It doesn't know where you are in advance, so it has no choice but to do all 1 million checks just to find your username. If the number of users double to 2 million, the same login attempt now requires 2 million checks. And this is where you start to see the scaling problem. Now, you might notice that checking a user's password takes 2 milliseconds or 4 milliseconds, and that detail doesn't really matter here. This is why you may have heard the rule that bigO of 2n is treated as bigO of n because constant factors don't change the growth pattern here. Think of it this way, if you're walking to a city 1,000 miles away, taking one step at a time or two steps at a time doesn't change the fact that the journey is still linear. You're not flying, which would be logarithmic, and you're not crawling either, which would be quadratic. So with bigO of n, the system scales linearly. It's not terrible, but it's not great for something as common and performance critical as a login system. Here is a better approach by using a hash table. This is bigO of one time. Whether you have 100 users or 100 million, it takes one operation. This is why major applications use databases with indexes. They provide bigO of one or bigO of login access. Now consider finding duplicate photos. A naive approach might compare every photo with every other photo. Now this is bigO of n squared. For 1000 photos, that's about a million comparisons. For 10,000 photos, it's 100 million comparisons. The problem isn't visible at small scale. For instance, if we have 100 photos, we will be doing 10,000 operations. It might be fine. At 10,000 photos, that is 100 million operations, it becomes a bottleneck. So what is the solution for this? By sorting list and then scaling, we handle 10,000 operations with about 40,000 operations instead of 100 million. So that gives us bigO of nlogn. Up next is bigO of login. In some cases, your data is already sorted. For example, you might need to find username in a sorted list. In such situations like this, binary search is used and it runs in bigO of login time. Let's see how this actually works in practice. Imagine you have 1 million users and the list is already sorted. Instead of starting at the beginning, the system jumps straight to the middle. It checks the user at the position 500,000. If the username you're looking for comes after that, the entire first half of the list can be ignored. Now you repeat the same process on the remaining half. You jump to the middle again, check one user and discard half of what's left. Each step cuts the search space in half. That's why even with 1 million users, you only need about 20 checks. Each step halves the search space. Finding any user takes at most 20 steps and not 1 million. This logarithmic scaling is why databases use indexes. Searching 1 billion records takes about 30 steps with a good index. Practical implications for scaling. Let's see what this means for user growth. Suppose each operation takes 1 microsecond. bigO of 1 gives 1 microsecond for any number of users. bigO of login is 20 microseconds for 1 million users. bigO of n 1 second for 1 million users, and bigO of n squared is 12 days for 10,000 users. This explains why startups often hit scaling walls. Code that worked fine with 100 users might fail completely with 100,000 users. One of the most famous examples of a scaling disaster is early Twitter. Back then, they used a monolithic architecture, basically one giant heavy engine called monorail that tried to do everything at once. The biggest problem was a process called synchronous fan out. Here's how it worked. If you tweeted, the system would immediately try to push that tweet into the timeline of every single person following you before it even finished sending. Now do the math. If you have 10 followers, the system does 10 writes. Easy. But as Twitter went viral, celebrities joined. If someone with 10 million followers tweeted, the system suddenly had to perform 10 million operations for just one click of a button. As both the number of users and their follower counts grew, the work didn't just add up, it multiplied. This massive bottleneck created the infamous fail well, the crash screen users saw whenever the servers were drowning in data. So, to save the platform, Twitter had to rewrite the rules. They moved to an asynchronous model. Instead of doing all that work the second you hit tweet, they handle it in the background. For giant accounts, they switch to a mix on demand strategy. They don't push the tweet to you, your app just grabs it when you open the feed. So by changing the architecture, they turned a multiplication of work nightmare into a streamlined process that always stays fast and consistent. Now, when different algorithms matter, you don't always need the most efficient algorithm. Consider data size. bigO of n squared might be fine if n is always under 100. Read versus write frequency. Optimize read heavy operations with bigO of 1 or bigO of log n. Hardware trade offs. Sometimes bigO of n with less memory is better than bigO of log n with more memory. The key is knowing which algorithm to use when. If you are building a feature that will scale with users, avoid bigO of n squared and be careful with bigO of n. bigO of 1 and bigO of log n scale well to millions of users. bigO of n can work if operations are infrequent or data doesn't grow too large. bigO of n squared becomes problematic around 1000 to 10,000 items. So bigO helps you anticipate the problems before they even happen. So if you are learning to code, practice identifying the time complexity. When you write a loop, ask yourself this one question: what if this list or an array had 1 million items? Comment on your thoughts about this concept down below in the comment section. Thanks for watching.